Greetings and welcome to this installment of lectures of Strength of Materials. And this lecture, as you can probably see, is about pressure vessels. The first question to ask is, what is a pressure vessel? So I just Googled some, and here's one, fairly large one. You can see that it's cylindrical and has these various doors and valves and whatnot. Now, these pressure vessels are used to store any kind of fluid, whether it's a gas or liquid, or a liquid with a gas, maybe at the top there. So there are a variety of them. So this one is obviously large and is on some form of trucks, probably going to go on a railroad somewhere. Here's a nice little schematic for a cylindrical one like that. Here's another one. Notice it's vertically oriented. This one has to do with some kind of nuclear reactor core. Now, this brings up a good topic that pressure vessels often have been used to store steam and used for steam power, which still powers a lot of our present day need for electricity generation. So this is, we might not power it with wood, but there's plenty of coal burning generators in the world. And here's some more vertically oriented ones again. Here's a pressure vessel. This one goes into space, and what we want to avoid here is getting any of those fluids out because there's nothing in space. So it's got to be pressurized on the inside for that. Here's another large one, and here's a really, really large one. So these pressure vessels have been used in a variety of situations. Let's just go back to this one here in terms of generating power. The ASME, American Society of Mechanical Engineers, was formed in part around the problems that they had with power generation in the late 1800s. You had many of these pressure vessels being over pressurized, and they would leak. Some actually exploded, spewing fire all over, say, a factory, and people were killed and stuff. So it was really important that these were better specified. So another one of my favorite places, Cornell University, played a role in founding the ASME. Right back here is the Sibley Hall, and that was a place where some of the first members got together and said, hey, we should really have an organization of mechanical engineers. So they eventually did get together at the Stevens Institute of Technology and founded the ASME in 1880, and the ASME boiler and pressure vessel code is used throughout the world to specify safe pressure vessels and boilers. So with that introduction, let's get to some of the material aspects of it. I'm going to draw a quick cylinder here representing our pressure vessel. And I'm going to cut it with this section cut. So what I have on the inside is a pressure P that's pushing out in all directions. And it's also pushing at the back here, inside the pressure vessel. So all over like that, like that. Now, the thickness here is the only thing keeping this pressure vessel from exploding. So to get a better view of this, let's go here. And right here, this is the thickness that has a force on it, pulling it back in. That's the force of the actual material that is keeping it in. Inside there is our pressure. And notice how our pressure is going against the wall over there, but also up over here and over to here and down here and so on. Well, these forces actually from this free body diagram kind of cancel each other out. So the only force left over is the one going against the wall. So if I go and show it to you like this, you'll see that we have forces to the left and forces to the right. Now, this stress is known as the longitudinal stress for a cylinder, or if it's a sphere, it would be spherical stress. So as you can hopefully imagine, if we just made this body length practically zero, we would be coming out of this wall here, which would make this effectively a sphere, and we would still have this same effective stress. Now, this force that is on this thickness here has to be opposed by the same force that's over here. So if we know what our pressure is inside here pushing, and the area, which is the inside area here, then we know that that pressure multiplied by that area is going to be a force, and that force has to be, again, opposed by the force that is on this material. So we have that force, and if we know the dimensions here, we can get that area. So if we have got the force and the area, we will know the stress in this situation. So let's go try to figure that out. Okay, let's draw this a little bit closer to what we were just looking at. And we've got the inner diameter here. Okay, and inside we have a pressure P. Then we have this force here. Now notice that our pressure now is P and not a applied force P. So the pressure inside, when multiplied by the area, the inner diameter, has to equal the force F. So we now have F times P times AI. Let's rewrite F as P times pi times the inner diameter squared all over 4. So we now have that as the force on this cross-sectional area. However, the stress on that cross-sectional area has to equal the force on that cross-sectional area divided by its area. So I'm just going to put AX here, because remember, this area here in the blue is going to be different than the inside area here in the P. So the only two things that they connect on is this relationship here is for the force. So let's calculate that out. Stress equals force over area, which is equal to the pressure P times pi times the inner diameter squared over 4 all over. Now this area here is pi times the outer diameter squared all over 4 minus pi times the inner diameter squared all over 4. Now this is starting to look a little bit messy, but luckily, using wonderful things called algebra, I've got pi on the top and pi on the bottom for both of these. I can actually bring this out, get rid of these guys, so I just have outer diameter squared minus inner diameter squared, all that times pi over 4, and I can cross these guys out. So I end up with P times the inner diameter squared all over the outer diameter squared minus the inner diameter squared. Now you might say that we're a little bit stuck because we've got this kind of stuff on the bottom, and well, I guess it's okay if we know these values, but we're going to simplify things a little bit. So if I've got P times di squared over outer diameter squared minus inner diameter squared, notice that the outer diameter is this thing. It's from here all the way to here. The inner diameter is right in here. So the outer diameter is the inner diameter plus two wall thicknesses. Notice that's 2 wall thicknesses. That's a common mistake, that the diameter, sometimes the people think, oh, just add the wall thickness. No, you have to add it twice for the diameter. So that's what we're going to do. So I'm going to change the outer diameter to reflect the wall thickness. Outer diameter is the inner diameter plus 2t, and that gets squared, minus the inner diameter squared. And when we take this and we square it, we get the inner diameter squared plus 4 times di times t. So we did FOIL. So we multiplied 2t times di, and we got 2 dit. Then we did it again because we used the outer and the inner. And then we square 2t. And we end up with 4t squared. Well, we have to still subtract the di squared from here, and we get to cancel that out. So di squared gets out here, and di squared gets out here. Now the assumption we make is that this thing right here, t, is small. Okay, it's fairly small compared to di, and then we're going to square it. So this is going to be a relatively small term, so we're just going to throw it out. Don't try this at home, but yes, it's fairly common to do this. So we say this is approximately P times di squared over 4 di times t, and squared gets canceled out with the di, and we end up with the longitudinal stress is approximately equal to the pressure times the inner diameter all over 4t. Thing is about these pressure vessels is that this isn't the only stress. This is only a stress in one direction. So if we think of the this axis going along here with that force as the x-axis, then going up this way would be the y-axis. The stress going along this axis is called the hoop stress. So we address that in a very similar fashion, and we look at maybe a slice here of a cylinder. Now a sphere does not have this kind of structure, so we don't have to worry about that for a sphere, but we have, again, this pressure here in this cross section, and we have a responding reaction force here only at these sections. So if I simply have this cylinder going, pretty much at infinity, long enough to make the end caps not really important, then we just can multiply this distance here, which is the inside diameter, by L to find some area. So this is di times L, and we multiply that times the pressure P, and we get our force. And then we have to make that equal to whatever force is on the wall in these locations here. So let's write that out instead. So P times di times L equals the force. Okay, so then we need to find our stress. So we say our stress is equal to our force over the area, and that's equal to the pressure times the inside diameter times L all over. Okay, so the area here is just going to be two of those wall thicknesses. So there's a thickness here and a thickness there, and then it goes particular whatever length deep it is. So the area that this force is over is 2 times the wall thickness times whatever length we're talking about, and luckily the L's cancel out, and we are left with our stress equaling our pressure times our inside diameter all over 2t. You can see that the stresses that are longitudinal, or for that matter in a sphere, are 1/2 that of what they are along the hoop. So this is why a sphere is the most efficient way of building a pressure vessel in terms of pure engineering. It pretty much effectively requires half of the wall thickness, so half the material, and of course it requires less material per volume as well. Now there are many reasons that we use cylinders, not the least being that we have to fit them places such as on railroad cars and the like, and they're just more convenient in many respects, but we can use these equations quite effectively to estimate what we need for wall thicknesses. Now, one thing is very, very important here. These are thin-walled. What does that mean? Well, remember how I said that this is close to 0? Because it's kind of really small. Well, what happens when it's not small? Okay, then we have something that's thick-walled. Also, we made a few other assumptions in here that all the forces were going to be evenly distributed. Well, when it's thick-walled, it's not. So what do we really mean by thin-walled? The question is that you have to ask is your wall thickness less than 1/10 of your inside radius, or for the matter, 1/20th of your inside diameter. So this is kind of the cutaway of the wall section that we were just considering, that were the hoop stresses. Notice how near the ends the stresses would come closer to what a sphere would be, but kind of in the middle here, those effects are not as important. So we would look at it more from this perspective rather than a spherical perspective. So this is our introduction to pressure vessels, focusing on what they are and how we can simplify them, analyze them, and look at thin-walled pressure vessels and what that means. I will have more videos that discuss thick-walled pressure vessels and some example problems for them.